Afternoon, everyone. Hope everyone's Friday is going well. Today we are just going to kind of continue with what we've been doing with kind of working with these Taylor series, specifically the big five that we will have memorized, or maybe you've already kind of at least memorized some of them. My notes did go longer yesterday, so I'm going to hold myself to just doing like 20-minute notes today. And then whatever we don't get done, we'll finish on Monday. Your series test is a week from today, but my goal is, of course, to finish everything by Monday. Tuesday, we know, is the ACT day for juniors, asynchronous for everyone else. I'm not really planning anything that day. Wednesday and Thursday will be kind of like review days, and then the test, obviously, on that Friday. So where we kind of left off at, so we had finished identifying the big five series. I can't emphasize enough, the sooner you get those kind of like memorized, the easier this last topic is going to be. And again, different things you want to have memorized, obviously the sigma notation, but then also the first four terms, because sometimes we'll be in terms, sometimes we'll be looking at the sigma notation. And where we had ended up with on yesterday is if we have a series, how we can manipulate it to find basically its formula using one of the known ones that we have. So go ahead for me just to start off as kind of a warm-up. Let's do one more where you have to kind of manipulate it to rewrite it. So again, I have write the Maclaurin series for f of x, which is equal to x over 1 plus x cubed. And I want you to find the Maclaurin series for that using one of the memorized series. And again, you could be doing it the long way, like you have your n column, your nth derivatives evaluated at the center, and then the terms. But for this function, it gets pretty messy finding the derivative over and over again, and then even a little bit more challenging to find a formula once you get to that point. So this is a good one to use that shortcut of kind of manipulating the series. So take a moment to kind of see, first off, you want to look at the big five, figure out which of the big five that one looks closest to. And then you can replace x with something else. And then you can also like multiply and divide on both sides to get it into the series that would match f of x. So take a second to do that, and then we'll go over it. And then we'll look at how we can kind of go backwards looking at some terms. So if we're looking at this one, this is a rational function. When you see a rational function, it is most likely going to be the geometric series. So what is that geometric series? Again, the geometric series is the 1 over 1 minus x, and that is equal to the series of just x to the n. So manipulating it, you can either do this in a single step or in one step. The first thing I notice is the function we want has a positive x cubed in the denominator. The one that we have is like a negative x. So what replacement can I do? I can substitute negative x cubed in for x. So if I go back and do that on the other side, I can plug in negative x cubed in for the x, and I should put the limits on this. And that works now because we know that 1 plus x cubed, we do have what we want. And then last step, we want to go ahead and multiply both sides by x. That's how that x is going to get in the numerator. So I do have this x, which is equal to 1 plus x cubed. And on the other side, we do want to simplify it, because remember, we always want it in the nice form. And the nice form is always going to be the coefficient times x minus the center to an exponent. And again, the center is 0, which in this case it is. We wouldn't need to worry about it. So if I think about simplifying all of this, I'm going to kind of go off to the side. One thing I always recommend doing is splitting off the negative as its own factor. So using some exponent rules, that's going to become -1 to the nth. X to the third raised to the nth is x to the 3n, and we multiply that by x to the first power technically. And so then simplifying it, I have a -1 to the nth. Those have the same base. What do we do when we have the same base? We can add them together. So what is a Maclaurin series for that function f of x? It is what we see on the right-hand side. I am going to add a little disclaimer to this one. The geometric series we know only converges when the absolute value of x is less than 1. So this statement is only true as long as x is in the interval of convergence, which I'm not going to find right now, but we do know how to find the interval of convergence, say if that was like a part B of this question, using the ratio test and then testing the endpoints. But for now, we can kind of stop there and say this is the series that is representing x over 1 plus x cubed. Questions on that one? All right, let's try one where we go backwards. So these were ones we had the function and we kind of manipulate the sigma notation. Another type of an example would be maybe terms, and you have to go backwards from there. So I have what function is modeled by this Maclaurin series. And we have this -x over 5 plus x cubed over 5 times 2 factorial. We see there's some like alternating terms. We see there's some factorials. We see x raised to a power. And we need to kind of figure out where to start off with. So we are going to use one of those memorized 5. And so when I think about them, we do have, of course, the geometric one. We have e to the x. We have the natural log of x. We have the cosine of x, and we have the sine of x. Those are the only 5 options we have in BC. Those are the only 5 options that we really need to consider. And different things that I use to kind of make my decision is I let the factorials basically inform me of which one to choose. What do I mean by letting the factorials inform my choice? I notice for these we have like 2 factorial, 4 factorial, 6 factorial. It has all of the even factorials in the problem. When we have the even factorials, which one of these functions has the even factorials? Where the geometric just has no factorials, definitely can't be that one. Natural log has no factorials, definitely can't be that one. The one that has the even factorials will be cosine. So I'm going to use cosine to kind of determine which one I need to use. You might be asking yourself, well, I see a bunch of odd exponents. Could it also be sine? And yes, sine does have the odd exponents, but it's going to be a whole lot easier to manipulate an exponent of x than it is going to be to manipulate a factorial. So we're going to choose cosine because that's going to be the best choice for this series. So since we're choosing cosine, I'm going to go ahead and write down what cosine is equal to. We know that cosine of x is equal to, and again, you will memorize this eventually if you haven't already. It is an alternating series. It has the even factorials in the denominator, and then x is raised to the even factorials as well. What's important for one like this, and that you really kind of think about the first few terms. Notice they gave you the first 4 terms here, so I'm going to go ahead and write out the first 4 terms of cosines. That is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th, and that's going to continue forever. And similar to what we did to those other ones, we want to turn this series into the one that was given. And you're just going to do like some basic algebra. I do say basic algebra, but again, we could do really any type of mathematical operation. As long as what you do to one side, you also do to the other. So you can multiply by x on both sides. You can multiply by a number of both sides. You can technically integrate both sides. You can technically take the derivative of both sides. Any kind of mathematical operation, this is an equation, so what we do to one side, we have to do to the other. And you can do this all in one step or a single step. I tend to do it like in multiple steps just to make sure I kind of hit everything. The first thing I noticed that all of these terms do have a 5 in the denominator. Well, how can I get a 5 in the denominator? I can just multiply by 1/5 on both sides of that equation. So far we have that the 1/5 of cosine of x is equal to, I'm going to ignore the sigma notation because I really just need to figure out the terms. So I have 1/5 minus 1 over 5 to factorial x squared plus 1 over 5 times 4 factorial x to the 4th minus 1 over 5 times 6 factorial x to the 6th, and that's continuing forever. So I've taken care of the 5s, and now we need to figure out what else needs to happen. Well, already looking at the numerators, I see it goes like x, x cubed, x to the 5th, x to the 7th. What can I do to both sides to create that in the numerator with what I have so far?
Multiply by x.
Multiply by x. And I am going to kind of combine two steps into one right here. So I'm going to multiply by x. I'm going to look ahead and kind of see what else I need. I notice the series that's given to me, it goes negative, positive, negative, positive. The one we have goes positive, negative, positive, negative. So if I want to combine some steps, instead of just multiplying by x, what could I multiply both sides by? Negative x. So I'm going to multiply both sides by negative x. And again, I could have done this all in one step. I could have just multiplied both sides by negative x over 5. So what we end up seeing is negative x over 5 cosine of x is equal to the series that we started out with once we multiply everything across. And you might be asking, like, well, how much of this will we need to show? Officially, how much you need to show is really not much work at all. Like, if you can identify what you're multiplying by and that's all you're doing, you can just jump straight to the answer. And basically, again, what we're saying is this function right here is represented by the series represented by that infinite polynomial. It didn't ask us to write the sigma notation, so we don't need to worry about writing the sigma notation, but we could have easily taken that sigma notation and multiplied it by negative x over 5 as well. But this is just asking what is it modeled by, and that would be your answer. Questions on that problem? All right, let's try at least one more. A lot of students look at these problems as we're doing them, like they feel like they're just kind of like making up stuff. And in some ways you are still kind of bound by like the rules of math, the series, these known ones. But you really are just trying to force something to happen. So just like you're manipulating it, you're using your algebra skills to force it into a form that we recognize and one that we can use. So looking at this question, we'll stop here for today. It says that this series converges and we want to find its sum. Thankfully, it did not ask us to determine whether the series converged. If it did ask us, just to review some stuff that we've done this week, you would have to use the ratio test and kind of go from there. But it's telling us that it converges, so we can just kind of assume, hey, it converges, there is a sum. And it tells us to find the sum. So we want to figure out what this series is equal to. It could be a function, it could be a number. We need to figure out what this series is equal to. Similar process when you're looking at terms. You want to look at the big 5. And I'm going to kind of write them off to the side again. And we need to figure out which of the big 5 is best modeled by this series that we see. So again, the general process I go through, I let factorials be my guide. I see an n factorial in the problem. The geometric one doesn't have factorials in it. The natural log function also doesn't have factorials in it. So from here, I do have to kind of make a choice. The cosine is the even factorials. The sine is the odd factorials. E to the x is the one that has all of them. So which function am I using? I'm going to use the series given by e to the x. So again, what have we memorized? We know that e to the x is equal to the series where n goes to from infinity up starting at 0, and it's 1 over n factorial x to the n. And again, we're just going to kind of manipulate what we have, and we know that what was given needs to look something like this, and then we can kind of do our relationships. So if I'm thinking about the one that is given, I know some things that are the same. So we have this 1 over n factorial. This one also has a 1 over n factorial. So if I wanted to figure out some things that it is equivalent to, let me just go ahead and rewrite it. So there's the thing that is the same. And then we have this 2 to the n in the denominator that was not the same. So then I look at what's left over. Well, the e to the x formula had this x to the n, so somehow I have to think about this as an x to the n. Well, pretty easy. How can we think of it like that? I have 1 over n factorial. That's the same thing as saying 1/2 to the n. Well, what is that 1/2? That 1/2 is in the same place where x goes. So kind of doing some substitution, what would this series be equal to? Well, where does the x go? It's e to the x. This problem right here is literally equal to e to the 1/2. And again, what are we basically saying? Because again, sometimes I think the meaning is lost. This is an infinite series. If you could add up all the terms of that series, they would converge and be exactly equal to e to the 1/2. And you can kind of see where we use that memorize rule and just matched up the corresponding parts to get to that 1/2. Questions on that? All right, so I said I only want to do 20-minute notes, so I am going to stop there today and keep my word. Monday when we return, we'll do another one just like that as a warm-up, where we will look at a series, figure out how to manipulate it, and write it as a known one. And then the rest of Monday, we'll look at some examples of just other types of problems that we can encounter with a series. So what I want you working on basically and kind of finishing out before Monday is, there we go. Your goal by Monday, I want you to have all of homework 7 done. I also want you to have all of homework 8 done. That will kind of just make sure that you're on track, and then that way all next week you can work on homework 9 and the briefcase binder. Remember, homework 2 is on 2 separate pages in OneNote. I already had a few people reach out to me and say that second page didn't show up, so definitely continue to reach out to me and I can make sure it does show up for you if it hasn't already. You can start homework 9, like if you're just trying to get ahead, but ultimately I will be happy, and I think you'll appreciate yourself if you finished all of homework 7 and 8 before Monday, so that when we kind of finish up these last topics of series, you're kind of like on the same page as me and everyone else. So Monday we'll kind of finish looking at these notes. Tuesday again is an ACT day, so it's kind of like an off day to kind of catch up on homework. And then Wednesday and Thursday will be review days for series, and then your series test is going to be on Friday. So at this point, like if you are good to go, then you can sign off, and I hope you have a good weekend. If you want to stay behind to ask any clarifying questions, then definitely don't hesitate to do that.